Okay, hello everyone. So welcome to this little lesson or consultation on electrolytic cell versus electric cell. All right, I think there's some confusion over these two concepts of electrolytic cell and electric cell. So let's hope that today's lesson will help to dispel some of the misconceptions that you have, will help to clarify some of the doubts that you have. All right. So let's begin. There are a number of words here. All right. Now, I hope you realize that there are two main types of cells. The two main types of cells are electrolytic versus electric. Now, the electric cell is also known as a chemical cell. And the electric cell or chemical cell is what you commonly call a battery. So these things are actually the same thing. Okay? So this is type number 1, type number 2, if you like. And these two are exact opposites of each other in every single way. So the electrolytic cell is the opposite of the electric cell. So these two will oppose each other. They will be the opposite of each other in every single way that we will see later on. All right. Now, the complication here is if you were to do a quick search online, your electric cells can be further subdivided into many different types. So if you do a quick search online, you will realize that electric cells can also be called simple cells, galvanic cells, voltaic cells. Fuel cells that we learn under energy changes can also be considered electric cells. Are they all the same thing? Well, the answer is in one short sentence. Yes, they operate on the same principle. What it means is that simple cells, galvanic cells, voltaic cells, fuel cells, they operate on the same concept. They operate on the same type of reaction. Okay? However, there are some slight differences between fuel cell and simple cell. So later on, at the end, we will address what is the slight difference between the fuel cell and simple cell. Okay, so at this juncture, can we have this common understanding that electrolytic cell is the opposite of electric cell? Secondly, the electric cell can be further subdivided into different types of cells, which all operate on the same principle. Okay, now in case you're wondering, why so many names for the same thing? So why so many names for electric cell? Because they are named after different people. So this is a bit of history. The galvanic cell is named after Galvani. All right. Okay, his full name is Luigi Galvani. All right, he's the Italian scientist who first experimented with frog legs. Okay, so he realized that frog legs, even after the frog has died, the frog legs will still twitch. Twitch means shake, shudder a little. Why? So he did some further experiments and found that, oh, this is because the frog legs contain nerves. Nerves carry electric currents. The electric currents therefore cause the frog legs to twitch. All right, and hence he is seen as one of the founders of electricity and the concept of an electric cell. Therefore, we have named one of the cells after him, galvanic cell. The voltaic cell is also named after another scientist called Alessandro Volta. Okay, and this is also the scientist that the unit volt is named after. So Alessandro Volta, like Luigi Galvani, is Italian. He's also one of the pioneers of electricity. All right, and that's why you also often hear voltaic cell. The voltaic cell is actually just a simple cell. The galvanic cell is also just a simple cell. It's just that it's named after a scientist. All right, so very often discoveries, innovations are named after different people. That's it. All right, so let's go deep now into the differences between electrolytic and electric. Remember, these are the two opposites of each other. So the first thing that is the opposite is whether you need external power source. External power source means, do I need to connect it to the battery? Must I put a battery into the circuit in order for this to work? It's quite obvious that an electrolytic cell has a battery connected in it. Therefore, yes, external power is needed for an electrolytic cell because a battery is connected. You will see a battery in the circuit, all right, for an electrolytic cell. And that's how you identify electrolysis. Electrolysis is identified because you can see a battery connected in the circuit. And so for electric cells, they are the opposite. No external power needed. They do not need to take in energy from external sources. All right. So remember that fuel cells are one type of electric cell. So fuel cells also don't need external power. Okay. So that's the first major difference between electrolytic cell and electric cell. So if we follow this point, electrolysis requires energy, power to be taken in from an external source. Electric cells do not need this external power source. So what do you think is the energy change? Is it exothermic or is it endothermic? So for the electrolytic cell, it needs an external power source in order for electrolysis to happen. So would you classify this as endothermic or exothermic? So if you need an external power source, that means you need to take in energy. Therefore, electrolysis, the reaction, the overall reaction is endothermic because it takes in energy from the surroundings, from the external source in order to work. On the other hand, remember electric cells are the opposite of electrolytic cells. It will be exothermic. Remember fuel cell is also one type of electric cell, so it's also exothermic. So the first 2 points are linked. If you need an external power source, that means you take in energy, therefore you are endothermic. If you don't need an external power source, you don't take in energy, you release energy, therefore you are exothermic. Now at this juncture, can we check that the first 2 rows are okay? You have understood it? If you have understood it, please give me a thumbs up. If not, you may wish to ask by unmuting yourself, or you can type in the group chat, okay, in the Zoom chat. Okay, I see a few thumbs ups. Okay, right. Now, let's add on to this point. I hope we remember endothermic means delta H is more than 0. Delta H is positive. Exothermic means delta H is negative. Okay. So this is just a link between the 2 chapters on electric cell and energy changes. Now, once we know whether it's endo or exo, right? We can start to work out the energy levels of the products versus the reactants. So if you recall, if the reaction is endothermic, it takes in energy from the surroundings. In this case, the surroundings is not just the air, the water. The surroundings for electrolysis includes the external power source that you have connected it to, includes the battery that you have connected it to. So in electrolysis, it took in energy. Therefore, the products have higher energy than reactants. Okay? So it's the product that has higher energy. Okay? So for electric cells, electric cells include simple cells, include fuel cells. It is the reactants have higher energy than products. Okay, so this links well with what you learn under energy changes. When you learn how to draw the energy level diagram for both endothermic and exothermic reactions. Okay? Okay, so there was one question that came in. So in an electrolytic cell, it takes in energy from the surroundings. It's endothermic. Isn't the energy only taken in from the battery? Yes. So the battery constitutes the surroundings. I am taking in energy from an external power source that is not part of the system. So the battery is considered the surroundings in this case. Okay. Now, if you recall under energy changes, we also tried to link energy to stability. Remember, when you have higher energy, you are actually less stable. So if we say that products have higher energy, so electrolytic cell products have higher energy, it means that the product is less stable. All right. So in electrolysis, actually what you are forming at the end, the product that you are forming is less stable. And that makes perfect sense. Because if you think back to electrolysis, when you electrolyze, let's say, molten sodium chloride, molten NaCl, you will get sodium and chlorine. Sodium and chlorine, the products, are less stable than the ionic compound, sodium chloride itself. Sodium doesn't want to be sodium. Sodium wants to lose that one valence electron to form Na+. So by electrolyzing NaCl, you are forcing Na+ to become sodium again. Therefore, sodium formed is less stable. Okay? Now, moving on to the next two rows, we move away from the energy change. We look at the polarities, the charges of the anode and cathode. And this is where you need to understand the concept quite well. Firstly, we need to know that anode is always oxidation. Now, regardless of whether it's electrolytic or electric, this doesn't change. So I would advise you to write this in a slightly different color. The anode is always where oxidation happens. This doesn't change. In fact, this is the same throughout, whether it's electrolytic or electric. Anode is always where oxidation happens. So N-ox. So then what's the difference? Well, in an electrolytic cell, the anode is positively charged. Why? This is because in an electrolytic cell, the anode attracts anions. All right, the anode attracts anions in an electrolytic cell. Therefore, it must itself be positively charged so that it could attract anions. Now, this logic is now going to be the reversed. In an electric cell, you will realize that the anode is actually the negatively charged terminal or electrode. Why? This is because in an electric cell, you are not attracting ions. What you are doing is you are looking at oxidation being a loss of electrons. And because oxidation is a loss of electrons, this is where electrons are being lost. Electrons are being produced, right? Loss of electrons means, let's say, for example, zinc loses electrons. Zinc loses electrons means the half equation looks like this. If you write the half equations out, you will immediately realize that, hey, electrons are formed, electrons are produced. Therefore, at the anodes of electric cells, electrons are produced. It's a source of electrons for the circuit itself. Therefore, it's negative because the electrons are negatively charged. Okay? Now, once you have solved this, then you will be able to do the next one. Cathode, you can imagine, is just the reverse. But you will realize that cathode is still reduction for both electrolytic and electric cells. So N-ox, anode oxidation, red cat, cathode reduction. Now, in an electrolytic cell, the cathode is a negative terminal, so it attracts cat ions. Okay? But on the other hand, in the electric cells, the cathode is the positive electrode. You might be asking why. Because you must think, in an electric cell, you are not attracting cations, anions per se. What you are doing is you are thinking of how the electrons flow around your electric circuit. So, for example, this might happen in your circuit, right? This is one of the possible reactions that could happen. Okay? As you can see in this half equation, copper, Cu2 plus, is actually gaining electrons. By gaining electrons, you are actually using up electrons. Gaining electrons equals use up electrons. So electrons are being used up. Because electrons are being used up, the negative electrons are going away. Used up. If negative electrons are used up, it's positively charged because the negative electrons are going away, used up. All right? Now we go on to the direction of the electron flow. Okay? Now, the direction of electron flow, you will understand it if you understood the anode and cathode. All right? Now, the direction of electron flow, regardless of whether it's electrolysis or electric cell, all right, must always follow a logical pattern. Okay? In an electrolytic cell, the direction of electron flow is from positive to negative. Why? It must always be from the oxidation to the reduction. Because oxidation is a loss of electrons. So even in electrolysis, the oxidation loses electrons means you produce electrons, which have to be now transferred through the wire, okay, to the reduction. But on the other hand, for electric cell, is the reverse. But you can see when I say it's the reverse, it means it's from the negative to the positive. But again, it's still from the anode to the cathode. Okay, so what have you learned from these 3 rows? You have learned that anode oxidation, cathode reduction stays the same. It's an unchanging golden rule. But what has changed is just the polarities, whether it's positive or negative. Now, as a student like you, I used to find this really confusing. Why is it that the polarities have to be different from electrolytic to electric? To be really honest, I only fully understood this after looking at it multiple times from Sec 4 all the way till JC2. One fine day, I finally drew this table out and I realized something important. And something important that allowed me to memorize it better. How do I memorize the direction of electron flow? Well, I've learned that electrolysis is endothermic, right? Electrolysis is endothermic. What it means is that it must take in energy. This means that the reaction is actually not easy to do. It needs to take in energy to force the reaction to happen, right? That's the meaning of endothermic. It takes in energy from the surroundings. So if you think about it, electrons, do they really want to go from positive to negative? Electrons themselves are negatively charged. Would they really want to go towards negative? Negative electrons, negative terminal, they actually don't attract each other. Negative doesn't attract negative. So to force the electrons to go from positive to negative, I clearly have to take in energy. It is clearly not something that will happen naturally on its own. So because I already know that electrolysis, I need an external power source. It's endothermic. This means the reaction is actually hard to do. I am forcing the electrons to do something it doesn't want. What do electrons not want? Electrons don't want to move to negative. And that's how I remember electrolysis, electron flow is from positive to negative. Because I know that this is what electrons don't like. This is what electrons don't want. They don't want to move to negative. That's why I need to take in energy in electrolysis. Okay? On the other hand, why is it that fuel cell, simple cell are all exo? They are all exothermic because if you look at the direction of electron flow, it is exactly what the electrons would like to do. Electrons are themselves negatively charged. Negatively charged particles should naturally be attracted towards the positive end. And that's how I remember in a simple cell, in a fuel cell, the direction of electron flow is from negative to positive, because this is a natural flow of electrons. So at this juncture, can I just have a quick poll amongst the participants in this Zoom meeting? Do we understand the direction of the electron flow? And if you have any questions, please ask. Okay, don't just memorize, all right? Make sure you can internalize, link each row together, hopefully. Okay, there's a short question just now Mr. So has mentioned. Products have higher energy. So this third row over here, products have higher energy than reactants. Why is it that when you have higher energy, you are less stable? Well, you think about it, if you have higher energy, it means you have more energy to react, right? If you have more energy to react, you are probably moving faster. You are probably moving more vigorously. So the products have higher energy means the products are more reactive. If something is more reactive, it's less stable. Okay? So the person who asked this question, are we okay? Do you understand why higher energy means less stable? Okay, so you must always remember this. Higher energy means less stable. It is a golden rule in chemistry as well. All right. Now, for the rest who didn't give me a thumbs up, is it because we still have questions about the anode, cathode, and electron flow? I would think these three are probably the hardest to understand. Okay, and probably the hardest to memorize as well. So I would strongly advise you to think it through, like what I have said. Okay, there's another question. So if the reactants have higher energy, does it react faster? The answer is yes. Generally speaking, when things have higher energy, they will react faster, they will react more vigorously, they will react more violently. And that is the reason why in chemistry as well as in physics, when things have higher energy, they are much less stable. Okay, so to the person who asked this question, is it okay already? Okay, now, can Mr. So move on? Can you give me a thumbs up if I can move on? All right, now, so now we have cleared the hardest part. The hardest part really is the polarities and the direction of electron flow. After you could understand that, the rest is actually quite easy. Now, in electrolysis, what is the energy change or the energy conversion? Now, this question appears quite often in your TYS, in your workbook. They'll ask you, describe the differences between an electrolytic cell and an electric cell in terms of energy changes. Now, when they ask you for energy change, what they mean is two things actually. Number one, is it exo or endo? Right? But number two, they are also talking about the type of energy conversion, meaning in an electrolytic cell, what energy is converted to what energy? So the fact that an electrolytic cell must be connected to an external power source tells you it uses electricity. It actually uses up electricity, means it starts off as electrical energy. From electrical to chemical potential energy. Why is it starts off electrical energy? Because you needed to wire it, you needed to connect it to an external power source. This tells you the starting point should be electrical energy. It is then converted to chemical energy. And if you recall right at the start of this session, I mentioned that electrolytic cell is the opposite of electric cell, meaning electric cell must be the opposite, right? It starts off as from chemical energy to electrical energy. And that makes sense. The simple cell is used to generate, produce electricity. That means the ending must be electrical energy. You are producing electricity. That means the energy is converted to electrical energy. Same for the fuel cell, because the fuel cell is actually a type of electric cell. So at this juncture, do you realize that the fuel cell and the simple cell are actually very, very similar because they essentially work on the same principles? Namely, a fuel cell uses an exothermic reaction. A simple cell also uses an exothermic reaction. The energy conversions in a fuel cell and a simple cell are the same. And do you also realize that electrolysis, electrolytic cell, is the opposite of electric cell in every possible way? And this is what you need to know. Okay, this will help you avoid confusion. Okay, at this juncture, are we clear? Are there any questions that you should ask before we move on to the very last row? The last row is there for a reason, which I will explain later. But at this juncture, do we have any questions regarding the differences between electrolytic and electric cell? You can type in the chat as well. The chat allows you to message me directly so I can see your questions. No, please don't feel shy to ask, okay? Any questions are fine. Okay, if no, can you please give me a thumbs up so I move on to the last row, which has no header over there? Okay, thank you. How about the rest? I see a few thumbs ups, but I'm not sure if the rest are there. All right. Now, the last two rows, you can see gray boxes. The gray boxes are not meant to be filled, okay? The last two rows really is about the difference between simple cell and fuel cell. Many students are easily confused between simple cell and fuel cell. All right. Now, I just mentioned simple cell and fuel cell, they are all considered electric cells. So whether it's a simple cell or fuel cell doesn't matter. It operates on the same principles, whether it's exothermic, whether it's the polarities of the electrodes, whether it's the direction of electron flow. There is actually no difference between a simple cell and fuel cell. There is only one subtle, slight difference, and that is a simple cell makes use of a redox reaction to generate electron flow. And it does not require chemicals to be supplied continuously. Okay, this is an important concept. A simple cell, a galvanic cell or voltaic cell, these are the same things. Simple, galvanic, voltaic, they are all the same things. The simple cell doesn't need chemicals to be supplied continuously to it. Why? Because the chemicals are already inside it. If you think of a simple cell, and I've put the diagram right at the top, the diagram of a simple cell shows you zinc, copper, dipped into an electrolyte, right? So you have zinc and copper dipped into an electrolyte. There is no need for chemicals to be supplied in or out continuously. It is self-contained, if you like. Chemicals don't have to be supplied to it. All the chemicals you need for the cell are already there. Zinc, copper, the electrolyte. Okay? However, for a fuel cell, it also makes use of redox. However, it requires a continuous supply of chemicals to sustain the redox reaction to generate electron flow. This is the only difference between a fuel cell and a simple cell. A fuel cell requires a continuous supply of chemicals, means the chemicals must flow in, flow out, flow in, flow out in order to sustain the redox reaction. Okay? Now, you might be wondering why? Why so special? Why is fuel cell so different? This is because we use different sorts of chemicals, right? The simple cell just makes use of two different metals of different reactivity, like zinc and copper, right? Zinc versus copper. Zinc is more reactive than copper. That's it. So all you need to do is to have two pieces. One piece of zinc, one piece of copper. That's it. There is no need for anything else to be supplied continuously into the cell. Just need two metals and an electrolyte. That's it. Okay, so let's go back to the diagram in case you are lost. The diagram shows you zinc and copper deep inside what? There is no need to add anything else to it. There is no need for zinc to be continuously supplied, right? It is just a piece of metal. Same with copper. There's no need for copper to be continuously supplied because it's a piece of metal. But the fuel cell is just different. If you look at the fuel cell, you need to supply hydrogen in. You need to supply oxygen in. If the supply of hydrogen and oxygen stops, the fuel cell also stops working. All right. So the reason why the fuel cell is different is because you have chosen to use different chemicals. And these chemicals, hydrogen, oxygen, they have to continuously be supplied into the system, or else the reaction doesn't happen. They are not solids. Okay? Can? So that's the only difference between a simple cell and a fuel cell. And there's a question that just came in. So is it that fuel cells release heat energy and simple cells release electrical energy? Well, let's look again at the diagram, shall we? The diagram will tell you what sorts of energy are actually released. If you focus on the diagram, don't you realize that what we are doing here is actually generating a flow of electrons? The electrons move in a simple cell from the zinc to copper, more reactive to less reactive, right? From the negative to the positive electrode. It's an electron flow. And same, okay, it's the same in a fuel cell. It has to go from the negative to the positive. So this is the direction of electron flow. So now that we have established that there's an electron flow, can it still be heat energy in a fuel cell? Electron flow is not heat energy. Electron flow is electricity. Electricity means electrical energy. And therefore, even in a fuel cell, the energy change is from chemical to electrical energy. All right? So let's not be confused. Our fuel cell is also generating electricity. Therefore, the energy change is to electrical energy. And that's why under the second last row, we have written this down. It's from chemical to electrical energy. Okay? And that's what fuel cells are used for. The fuel cell is used to generate electrical energy for your devices to work, for your cars to move. It doesn't generate heat energy. Heat energy, in fact, is not desirable in the fuel cell because if it converts to heat energy, it actually causes less electrical energy to be generated. And therefore, your fuel cell is actually less efficient. Okay, there's another question that come in. For simple cell, I use zinc, I use copper, right? Mr. So said, oh, you don't need chemicals to be supplied to it continuously. I don't have to keep on adding zinc to it. But surely over time, the zinc will slowly react away. Yeah. Mr. So said, right, just now, zinc will form zinc 2+. It's oxidized, right? So zinc solid becomes zinc 2+ aqueous. You can see the half equation on the screen. So won't the zinc be used up slowly? The answer is yes. The simple cell that uses zinc and copper, the zinc will be oxidized slowly. Meaning you need to replenish the zinc after some time. But the keyword here is after some time, right? You don't supply zinc continuously every second. You will only change the electrodes perhaps after every week, after every month in a simple cell. And that's why it's correct. It's still correct to say that in a simple cell, it doesn't require chemicals to be supplied to it continuously. Okay, so the person who asked this question, is it okay? Do you understand this? Okay. Now there's one last question that come in. One person said, oh, it's an exothermic reaction. Doesn't it mean that heat energy is released? Okay, this person is referring to the fact that simple cell fuel cell are both exothermic, right? So didn't we learn, oh, exothermic means heat energy is released to the surroundings? Actually, the answer is yes. At O level, you have learned that exothermic means heat energy is released to the surroundings. But in reality, right, in chemistry, exothermic can also mean that energy in general is released to the surroundings. Need not just be heat, could be light, could be electrical. Okay? So if you go on to do more chemistry, you will learn a more correct term, okay, which is called exergonic. Okay, but let's not go into the actual definition of exergonic now. For now, you can take it that exothermic also automatically means that other forms of energy besides heat could be released to the surroundings. Okay, so for the person who asked this, do you understand this? All right. Okay, so the rest, do we have questions or not? I'm receiving questions from a few people, as you can see, and it's answered immediately. So if you do have questions, it's better to ask now. Okay, there's one more question that came in. The fuel cell makes use of hydrogen and oxygen, right? So you have learned that the fuel cell is hydrogen plus oxygen forms water. Now, can this heat energy be converted into electrical energy? Well, firstly, I'm glad you realized that hydrogen plus oxygen forms water. This is the overall equation in a fuel cell. Okay? But we are doing it in a way that separates the hydrogen and oxygen, right? By separating the hydrogen and oxygen, we are preventing them from reacting directly with one another. Do you realize that hydrogen is only at the anode? Oxygen is only at the cathode. They are physically separated, and that's the key. When it's physically separated, the hydrogen doesn't meet the oxygen directly. If it doesn't meet directly, then you don't release heat energy. We force the electrons from hydrogen to go to oxygen via a circuit. And that's how we generate electricity through the circuit. So this is a clever way of ensuring the electrons go through the circuit as electrical current, electricity, and doesn't generate heat. All right? If it generates heat, then you lose the electrical energy. Then the fuel cell is not as useful, not as efficient. So in short, the fuel cell should not have any energy converted to heat where possible. Because if it's converted to heat, that means your fuel cell is less efficient at producing or generating electricity. Okay, so to the person who asked this question, I think you have the misconception that hydrogen plus oxygen is as if they meet directly. They do not meet. Yes, the overall equation is H2 plus O2. But the reality is you are forcing the H2 to be at one electrode. You are forcing the O2 to be at one electrode. They are spatially separated. They never ever meet. And because they never ever meet, the electrons have to flow into a circuit. And that's useful for us. Because when electrons flow into a circuit, that's electrical current. All right? So to the person who asked this, I hope I've clarified that misconception. Okay, there should not be heat. Now, how do you actually learn this? If you think about your own handphones, if your own handphone battery is heating up, is that normal? Is that desirable? Okay, so previously, right, my handphone was about to spoil. How did I know that my handphone was about to spoil and give way? Was because when I actually used the handphone to watch, let's say, YouTube, the battery will heat up massively. Batteries aren't supposed to heat up. If batteries heat up a lot, that means a lot of heat energy is produced, right? Then it's not normal. It means that the battery, the simple cell inside, is actually malfunctioning. A simple cell or a fuel cell should ideally have minimal conversion to heat energy. Okay? Okay, so it's exothermic, okay? The reaction is exothermic. So we have one more question. Fuel cell is exothermic. How I know it's exothermic? Because I do not need external power source. It doesn't take in energy from surrounding. If it doesn't take in energy, that means it must give out energy. So if it gives out energy to the surroundings, that's exothermic. Now, I think the confusion here is that at O level, we tend to restrict it to heat energy is released, right? But in reality, exothermic could also mean in general that energy is released. Okay? May not necessarily be heat only. Okay, so fuel cells, the reaction is still exothermic. Just that, the energy is converted to electrical energy, not heat. Okay? And this is why electrochemistry, electric cells are smart. They are a good invention because you have now managed to harness the energy. You have managed to harness the energy as electrical energy so that you can make full use of it. If it's released as heat, very often that is not very useful, right? Heat is often not super useful in the context of modern inventions. You don't want your handphone to heat up. Ideally, you don't want your cars to heat up as well. So if you can harness and convert the energy to some other form that is useful, that is good. That's better, right? Okay, so now we have covered a lot on this one page. Can I just check? Are we okay? Okay, if you are okay, can you give me a thumbs up, please? Okay, good. Now I know it might be a bit taxing to listen to this bulk, so let's take a few seconds to digest what's on this page before we move on to the next part, all right? Okay, now let's move on to the next part. Next part is easy. Okay, you can see I wrote different types of simple galvanic voltaic cells. Why do I put slash slash slash? It means these three words are the same thing. All right. Some of you are confused because you searched online. Wow, one website wrote simple cell, one website wrote galvanic, one website wrote voltaic. Actually, they mean the same thing. All right. And so you can see I'm going to use these words liberally throughout this. We're going to look at just different examples. As we look at each example, let's try to figure out what is the anode, what's the cathode, and what's happening. All right. Now, some of these examples look very confusing, but let's break it down slowly. How do I break it down slowly? Well, as with any electrolysis question, it's always good to think through what's the anode, what's the cathode. Okay. Now, you know it's a simple cell. A simple cell makes use of two metals, right? One is more reactive, the other one is less reactive. The more reactive is the anode. The more reactive metal is always the anode. Why? Because the more reactive metal is the one that will lose electrons more readily. More reactive metal will lose electrons more readily. So like sodium. Sodium is super reactive because it really wants to lose that one valence electron super readily. On the other hand, copper is much less reactive because copper has a lower tendency to lose electron. Okay? Now, the anode in this case is quite easy, quite straightforward, right? Now, but if you recall when Mr. So taught you electrolysis, I also taught you should probably write down the ions present, right? Now, this also applies to any electric cell. Whenever you deal with electric cells, you should also make it a habit to write down what the ions present are. So in this case, you have zinc sulfate, so Zn2 plus, SO4 2 minus. On the right-hand side, you have Cu2 plus, SO4 2 minus, because it's copper sulfate. Okay, so now it's important to think through these ions you have. But these are not the only ions, right? They are all aqueous. If they are all aqueous, clearly you also have the added complications of H+. Now, this is exactly the same as electrolysis in the sense that this analysis forces you to write down what ions there are. Okay? Now, the purpose of writing out is so that, of course, you can predict what will happen next. Okay, so at the cathode, you might think that, oh, at the cathode now, is it going to be copper that's reacting? Or is it going to be H+? Am I going to see bubbles of hydrogen gas? How do you know? The only way to tell is really to look at the electrolyte. The electrolyte at the copper side is literally copper 2 sulfate. This means that in addition to H+ in the water, you also have Cu2+. So now you're going to decide for yourself. Is it going to be Cu2+ that's discharged or H+ that's discharged? Clearly, if you go by the electrochemical series, it's going to be Cu2+. Because Cu2+ is lower in electrochemical series. Okay? So Cu2+ is preferentially discharged. Okay? Another way to see the reaction at the cathode is, oh, because the electron go to copper, so copper doesn't lose electron. Copper must stay as copper. Okay, so there's no Cu2+. There should only be copper, copper, copper throughout. Okay? Now, if you summarize this, the overall equation, of course, is just Zn plus Cu2+ forms Zn2+ plus Cu. And this is just displacement, right? So now, just now, one student asked, fuel cell, how come got no heat energy? Because you are forcing the electrons to flow through the circuit. You're forcing the electrons to flow. That's why there's electricity, right? So in this case, it's the same. The galvanic cell is quite similar, right? Zinc and copper 2+, technically displacement should occur. Why is it that there's still electricity? Do you realize the zinc and the copper are spatially separated? They are separated for a reason, because if it's separated, then the zinc never meets the copper 2+. If it doesn't meet it directly, then there's no energy released as heat. You are forcing the energy to be converted to electrical energy. And that's why it's useful. All right. So same, galvanic cell, you should not have heat energy being released. What you should have is as much electrical energy being released as possible. Okay. Now, this one looks a bit different from our notes, right? How come there's this thing called a porous membrane or porous disc? Why is it that one side is zinc sulfate, one side is copper 2 sulfate? Our notes use sulfuric acid. It's different because this galvanic cell is slightly more complicated. It's slightly more complicated not because of zinc and copper. It's slightly more complicated because it uses different electrolytes on each side. One side is zinc sulfate, the other side is copper 2 sulfate. Now, why do we usually do this? Why do we bother to make the electrolyte different on both sides? There are a few possible reasons. One possible reason that Mr. So can think of is sulfuric acid is acidic. It may not be so safe to handle, especially if this needs to be inside some device, some appliance. It may not be good to have acids inside it. All right, so that's one reason. Another reason that I can think of why do we use different electrolytes on both sides, okay, is, as you can see, perhaps by using electrolytes, different electrolytes on both sides, okay, I can choose a wider variety of electrolytes. Previously, I had to choose sulfuric acid, but maybe now I can work with a different variety of electrolytes, which allows me to lower the cost of my device. Remember, all these things are ultimately meant for an application. They're not just theoretical, they are meant to be inside an appliance, a device. So to lower my cost, I can actually use different types of electrolytes, which could be cheaper. All right. Now, you notice that the porous membrane only allows N ions to flow through. This means that positive ions don't flow through. Okay. And that's crucial, right? You don't want the zinc and copper to meet. Because if zinc meets copper, like Zn meets Cu2 plus, then displacement occurs directly. Then it won't be useful. You want the electrons to flow in a circuit. You don't want electron to flow directly from Zn to Cu2 plus through the solution. You want the electron to flow through the circuit only. All right. Now, part B is similar. Example B is called a Daniell cell. Okay, one more word for you to remember. Daniell is, of course, named after someone, a person. So the Daniell cell also makes use of copper and zinc. It is exactly the same reaction. The anode is this. Zinc becomes Zn2 plus. And the cathode is also the same. Cu2 plus becomes Cu. Okay, I keep writing this wrong today. Okay, the reactions are exactly the same. The Daniell cell is exactly the same as just now. The only difference now, of course, is there's something called a salt bridge. So instead of membrane, we use salt bridge. Now, why do you need a salt bridge? You might be wondering, what's going on, right? If you think about it, the zinc forms Zn2 plus, right? This means that on the left-hand side, you have Zn2 plus being formed. Now imagine you got so many Zn2 plus. Zn2 plus is all positive. So does it mean that the left-hand side will become positively charged and more positive with time? Is that sustainable? The answer is, of course, no, right? Your solutions must remain electrically neutral. So one way for it to remain electrically neutral is for the Zn2 plus to slowly move up the salt bridge, and for the negative ions to move down into the solution. Now, the salt bridge can be made of many things. Usually, we use sodium nitrate or sodium sulfate. So what happens is that as the electric cell works, okay, there's more and more Zn2 plus produced on the left-hand side, so it's positive, right? So to neutralize these positive charges, the sulfate ion moves down into the left-hand side. It will not affect the electric cell's reaction. What it does is just to maintain the electrical charge balance. Okay? Now, part C is a voltaic pile. Wow, again, another complicated word, right? But if you think about it carefully, isn't it just zinc and copper again? It's literally the same thing, right? Zinc, copper, two different metals with different reactivities with sulfuric acid in the middle. So anode, zinc again. Zinc is more reactive, so loses electrons. But now the cathode is a bit more peculiar, right? So just now one student asked me, oh, why is it that in our notes, right, the cathode is H plus being discharged? Why not Cu2 plus? But now Mr. So tell me it's Cu2 plus for the first two. Yeah, like it's Cu2 plus for the first two because the electrolyte is copper sulfate. Right? If the electrolyte is copper sulfate, that means it has Cu2 plus and H plus. So between Cu2 plus and H plus, of course, Cu2 plus is selectively discharged. However, in a voltaic pile, it's not copper sulfate. You're using sulfuric acid, which is to say there is no Cu2 plus. Okay? If there's no Cu2 plus, it must now be H plus. Okay, so the voltaic pile is actually your first battery. The first battery was made by Alessandro Volta, and this is the first battery that was made by him, the voltaic pile, named after him. So to the person who asked the question just now about how come here is hydrogen gas, do you understand now? Whether you get hydrogen gas or whether you get copper depends on the electrolyte. Can? So if the electrolyte is copper sulfate, then you get copper. If the electrolyte is, in this case, sulfuric acid, you get hydrogen. Okay? So that's why it's important to pay attention to what ions are present in your electrolyte. Okay? So let's move on to the last one. I think is the last one. Oh yeah, last one. Okay, let's move on to the last one, shall we? Now the last one is interesting. I put a question mark there some more. The oldest battery discovered, question mark, because we don't know for sure. In fact, if you Google it later, the Baghdad battery, if you Google these words later, you'll realize that there's actually a lot of controversy over it because people aren't sure how this actually worked. They are not even sure if the ancient civilizations use this as a battery or not. Because electricity is something that's discovered quite recently, right? It's not something that existed 2,000 years ago. But this battery is estimated to be 2,000 plus years old, you know. Okay, this was discovered in the 1930s, but as of 1930, it was already 2,000 plus years old. Can you imagine how old this is? Now, this is called a Baghdad battery because it was discovered near Iraq, in Baghdad. Sorry, not near Iraq, in Iraq, in Baghdad. All right. And it was used by ancient civilizations 2,000 years ago. So this might actually be the first battery, and you can begin to see how this works. How does this actually work? Well, number one, iron, copper. You can immediately see, oh my goodness, this is some simple cell, right? This is like two different metals, iron and copper. One is more reactive than another. Immediately, you should be able to tell me anode, cathode. Right? It's a simple cell. It has two metals, different reactivity. The anode must be the more reactive metal, which in this case becomes obvious. It's iron. Iron is more reactive than copper, so iron will lose electrons and be oxidized more readily. So Fe becomes Fe2 plus. Okay, Fe usually forms Fe2 plus first. It won't form Fe3 plus immediately, if in case you're wondering. Okay. So the anode iron is oxidized to iron 2 ions. So what is the cathode? Again, is it Cu2 plus being reduced to copper, or is it H plus being reduced to hydrogen? It depends on the electrolyte. Obviously, 2,000 years ago, the ancient civilizations wouldn't know chemistry. The ancient civilizations wouldn't know copper 2 sulfate, zinc sulfate. So what did the ancient civilizations use as electrolytes? They have to use common liquids and solutions around them. One common solution is called vinegar. So it is actually hypothesized that the ancient civilizations added vinegar into this battery. Vinegar, the chemical name is otherwise known as ethanoic acid. Even if you don't know ethanoic, you should know acid. Acid contains what ion? Acids all contain H plus. So the ancient civilizations had made use of vinegar, poured it into the battery. Vinegar contains H plus, therefore it forms hydrogen gas. And this is wonderful because if you think about it, vinegar is so readily available. This battery works just by pouring vinegar in. All right, that's how amazing it is. And if you calculate the overall reaction, it's quite obvious. It's basically iron plus 2H plus forms Fe2 plus H2. Do you realize this is almost like iron reacts with acid? Iron plus acid forms salt and hydrogen, right? Do you realize that the beauty of this is that the iron does not directly react with the acid? Can you clearly see that the acid, the electrolyte, okay, is actually separated from the iron? And that's the beauty of it. Okay, so this is actually the oldest battery discovered. Scientists unsure for sure whether this was used as a battery or not. They are not sure if, the ancient civilizations didn't know how to use this to power up light bulbs. I don't think there were light bulbs 2,000 years ago, but perhaps they might have used this for other purposes. Okay, Ken? So at this juncture, A, B, C, D that I've just gone through, they are all simple cells because they make use of two different metals with different reactivities. All right. The only difference between these cells, these examples, is just what the metals were, what the electrolytes were. So it's important that you recognize that it's a simple cell because it's two metals of different reactivities, number one. Number two, you need to know that the more reactive metal is the anode. That's where oxidation happens, all right? Which means the less reactive metal is the cathode. Next, you need to work out, so what is the half equation to write? For the anode, it's easy. The more reactive metal is oxidized, so that's very easy to write. However, for the cathode, it's not so easy because you need to think what is inside the electrolyte. That's why don't ever forget to write down the ions present in an electrolyte because that will help guide you. Is it copper that is formed at the cathode or is it hydrogen gas that's formed at the cathode? It all depends on what's inside the electrolyte. Okay, so with this, we come to the end of today's consultation. I shall stop the recording here. Thank you.